magnetic field electric current and symmetry. We're going to try to use symmetry some now. So here's because electric fields can diverge, we needed a three-dimensional situation. We had a three-dimensional situation. The electric field points away in all directions, so we need to wrap it in a two-dimensional surface that binds, encloses a three-dimensional volume. Magnetic field lines have an additional constraint. They do not diverge. That's what Gauss's law for magnetic fields says, that the net flux is going to be zero regardless. So there's no reason that we need the higher dimensionality of Gauss's law. We already have them sort of constrained in a smaller, habitat. Magnetic field lines are planar. At least for symmetric current distributions. Always with the symmetry. So what if we just take a dimensional step down? Because we have it's more well behaved in a certain sense than electric fields. And when we're sort of seeing that working through the problems that we've worked through, they resolve much more neatly than the electric field calculations we were doing. So what if instead of a surface bounding a volume, so a surface is 2D, so what if we just talk about a curve, a line, a path bounding an area, right? Instead of a surface wrapping a volume, what if it's a line bounding an area? And I'm going to try to argue here that we're not interested in the outwardness of the magnetic field because it isn't outward. It's not radial. It's tangential everywhere. How does that help us? Suppose we calculated the indicated path integral, the indicated line integral, B dot dl. Now think back to the definition of work, force dot dl. This is the same thing. Same idea. Now, because this is a long, straight conductor carrying constant current, we already know the field. We already know B. It's mu 0 I over 2 pi r. And it's tangential. dl is tangential as well. They're parallel. The dot product is just going to be the product of their magnitudes. So we're integrating mu 0 I over 2 pi r dl around a circle. Everything's constant except dl. We integrate dl, and that's the circumference. So it's mu 0 I over 2 pi r times the circumference, 2 pi r. We're just going to get mu 0 I, like the slide shows. I just happens to be the current passing through the plane of the loop. There is no thing making a loop here. This is a path, an integration path. It's an Amperian loop, just like we talked about a Gaussian surface. It's an imaginary circular loop around which we calculate a path integral. And we seem to get, at least for this really nice case, we seem to get a relationship that sort of depends on the current passing through the surface bounded by that Amperian loop. Change the current, we change the answer. Change the size of the loop, nothing changes. All that we care about is how much current passes through the loop. A bigger version of what we just talked about. What if we walk the other way? What if, so the current comes out of the page at our face. So our thumb points back at our face and our fingers curl, as I'm looking at it, counterclockwise. What if, now if the integration goes counterclockwise, if the path that we take around the circle is also counterclockwise, then the field and the path are parallel, and it's the situation we just talked about. But what if we go the other way? That's fine. Now they're anti-parallel. The field still points counterclockwise because the right-hand rule. We just walk the path backwards, and now the direction we're going and the field are anti-parallel, so we end up with a minus sign. All right, now, what if we walk in a path? Does it need to be a circle? What if we walk in a path so that near a current carrying conductor, but so that the conductor doesn't pass through the surface enclosed by our path? It's an odd choice for the Amperian loop, but the more you stare at it, the more it makes sense. Radially, if we move away from the current or towards the current, as we do on path D to A and also on path B to C, the magnetic field is tangent but we're moving radially. So this dot product is going to get us a 0. These radial paths don't contribute anything to the path integral. The outer path from A to B, we are walking dl in the same direction as the magnetic field. So we're going to get a positive dot product. The field is mu0 I over 2 pi r. The particular radius we're talking about is r1. But the length of that path, in this case, it's 90 degrees worth of circular arc, is a quarter of the circumference of a circle r1 big. So the axial dependence of the magnetic field is going to be canceled by the circumference of that particular path, or the circular arc length of that path from A to B. A completely analogous situation is going to happen as we go from point C to point D on the inner tangential path. But here we're walking opposite the magnetic field. The negative dot product on the inner path and the positive dot product on the outer path will cancel, and the result will be 0. Which means I'm going to circle back to this statement. The path integral in a closed path is apparently related to the current that passes through the surface bounded by the path. It doesn't need to be a circle, just like technically Gauss's law didn't require that we use spherical Gaussian surfaces. It's just, if we do, the math turns out nice because we can leverage the symmetry, but we don't have to. The net flux, the net electric flux through any surface bounding a volume is only proportional to the amount of charge enclosed in that volume. Same story here. The net path integral. I'm gonna call integral, like closed integral b dot dl. I'm gonna call that. I'm gonna borrow from the 6 Ideas textbook and call that the circulation. So we say the electric flux, the net electric flux through a closed surface. Here I'm talking about the net magnetic circulation around a closed path. Here is apparently only related to the amount of current passing through the surface bounded by the path. Just like Gauss's law. If Gauss's law is equal to 0, that doesn't mean that the field is 0. It just means that the net flux is 0. Same story here. If the net circulation is 0, that doesn't mean that the magnetic field itself is 0, only that there is no net current passing through the plane bounded by the loop. All right. What do you think? What questions do we have? No questions? Okay, we're almost done. I'm going to leave this to you to show. A cylindrical conductor with radius r carries a current I. The current is uniformly distributed over the cross-sectional area of the conductor. So we could talk about a current density, and current I is equal to JA. Just the product. We don't need to like integrate or anything. Okay, to find the magnetic field at all radial points, we consider Amperian loops, one within the material out to some small radius r, inside the larger radius capital R. And we do the same thing again. We consider an Amperian loop outside the cylindrical conductor, and we end up with the typical result for the magnetic field outside a long linear conductor. This should feel very familiar. We know what the answer is outside the cylindrical conductor because we wrote it a few slides ago. The only thing we got to worry about is the field inside the material of the conductor. As we use larger and larger and larger loops, we're enclosing more and more and more of that current passing through the plane bounded by the loop. Okay, so the field increases up until we get to the radius of the cylinder, and then outside of that, it's like it's like we're a distance little r away from a very, very, very thin linear conductor, which should, I mean, this feels like the same stuff we were doing with Gauss's law, just with slightly different geometry and a different, it's a different field and a different expression, but it's the same method. To find the field inside a solenoid. Now, solenoid is a word that we've seen before today. That's what we were talking about when we looked at the experimental equipment at CERN, the Large Hadron Collider. Our circulation loop encloses a handful of the windings of this coil. Current passes into the page on the top and out of the page on the bottom of the left-hand drawing. If the left-hand drawing doesn't make you think a little bit about the electric field between two parallel plates, each loop contributes field perpendicular to the plane of the loop. Each leg of the Amperian path that is perpendicular to the magnetic field produced by all of those loops. Now this X and this dot, that represents an into and out of circle. It's one of the helical windings, where sort of there's a little bit of an approximation there that they are, vertically aligned. But if we use thin enough wire and we wind it tightly enough, that's a pretty good approximation. Into out of the field points to the left, as shown in the picture. Okay, cool. But these paths, B to C and D to A, are perpendicular to the field. So the circulation, the path integral along those paths is 0 because the dot product needs them to be parallel. Just outside this arrangement, just to the other side of this solenoid, the field is 0 because you can imagine that these are currents coming out of the page, and these are currents going into the page. Each one of these would produce a field that way, but each one of these would produce a field the other way. And on this path from C to D, the field is 0 anyway, which this feels almost exactly like how we determined the electric field between two parallel plates. I'm just saying. Along path A to B, we are walking in the direction of the magnetic field. So the dot product is positive, and the net dot product around the closed loop is positive, and it is related to, according to Ampere's law, to the total current enclosed, which is 1, 2, 3, 4, 5. It's the number of turns enclosed by this size loop, a loop of width L. So if this thing is wound tightly so that there are n turns in L horizontal space, multiply that by the current passing through it. There's this many per unit length times the current times mu zero. We're done. Mu zero Ni, where N is the number of turns per unit length. Notice, compared to the geometry of the solenoid, this magnetic field is roughly, out here we've got like edge effects, just like we had edge effects for, finite size square plates. If we let the solenoid become very long compared to its other dimensions, these edge effects are negligible, and we're looking at a very, an appreciably uniform field, at least for a pretty big, it's like half, it's the middle half of the length of this particular solenoid. Which answers the question, how are we going to get a uniform magnetic field to use in our MRI machine? And since it depends not only on how much current, but on the number of windings, the more tightly we wind the thing, the better return on our current investment we're going to get when we're trying to set up magnetic field. Later, I will post, I'll enable this lecture recording in Zoom, in Canvas, so that you can see it. But I'll also post these slides, and this video tutor solution here is one that I would definitely check out. I'm not gonna, it's a video, and I'm gonna let you watch that on your own time. But there've been a couple of them, and I would definitely go back and click through and watch those videos.